All right, so yesterday we left off and we were talking about applications of uniform circular motion, and we were just getting ready to watch a bunch of Chris Hadfield's videos on the effects of weightlessness on not just the human body, but just some like convenience things that we take for granted on Earth. Okay, zero gravity is not just a health concern in terms of what it can do to your body. It can be a health concern in terms of things that just don't work right. Okay, in zero gravity or work the way we expect them to. Right? For example, can you have running water on the International Space Station? No, you can't. You can't have a sink. Okay, because the sink depends on gravity to remove the water. Okay, it goes down the pipes and into the sewer system because of gravity, not because of anything else. You open up a tap under pressure in the International Space Station and you got water everywhere. All right, now you've probably all done this at some point in your life, but you were drinking something and someone made you laugh and it came out your nose. Okay, that can happen to you in zero gravity if you inhale any fluid. If it's just floating around, you can inhale it, right? And that's a pretty major problem. Okay? In fact, they have to have constant filtration of the air in order to make sure that particles are not floating around in the air that they could aspirate. Okay? This is what can kill people who have alcohol poisoning. Right? If you've drank too much alcohol and you pass out before you vomit, okay, then if you're flat on your back and you vomit, okay, the vomit will go. I've actually like up, and it goes right back down, and you inhale it, okay, and it's acidic and it burns and destroys your lungs, okay, and that can kill you. Right? You essentially drown in your own vomit. That's like probably right up there on like inhaling molten rock as ways I don't want to die. Okay, I have a list of ways I don't want to die. That's one of them. Okay. Well, that'd be quick, but I think it would be unpleasant. I don't know. I'd fall in a volcano. These are the dark things I think about. Probably, but I don't know, and I don't want to find out. That's why it's on my list of ways I don't want to go. No. I want to live forever. Yeah. Some people say, well, that might get boring. I'm like, well, I'll find out. So what we got to think about here, guys, are some of the kind of health problems associated with not having gravity around to remove stuff. Okay, we just take for granted. We drop something, it falls, and it's on the floor. The floor will get it. Okay, and then it's kind of out of the way. In fact, this happened to Chris Hadfield. I was watching an interview that he did shortly after he returned, and he'd gotten so used to everything not falling that he was talking to the person interviewing, and he had like signed an autograph or something, and he went like this with the pen. Because he just expected the pen to stay there, because for the last 6 months, that's all he had to do with the pen. Just, nope, no, the pen will stay there. And then he watched, he did that and let it fall, and he's like, jeez. Like he was so embarrassed that he'd actually done something so silly. Okay, but he had just gotten used to the fact that things just didn't fall. Okay, where he was. But when things don't fall, then you can inhale them. And there's all kinds of things that we as humans kind of leave behind. Okay, I mean, if you're on the International Space Station for a long period of time, you're going to have to get a haircut. Okay, you're gonna have to, shave. All of that stuff's got to go somewhere. Okay, clipping your nails. I mean, do you want to inhale somebody's fingernail or toenail? I don't. Okay, I think that's disgusting. Okay, but I mean, at least on Earth, when you clip them, even if they jump, they still fall on the ground, and I don't have to worry about breathing them in at some point. Okay, you do if you're in space. So we'll watch a few of his videos here just to see kind of the effects on the senses, the effect of having to be in zero gravity. All right, so obviously being in zero gravity, while probably initially novel and cool and fun, isn't good over the long term. So we got to come up with some way to create artificial gravity, right? And as we've seen in most kind of modern science fiction movies, okay, the way to do that is to have a spinning drum. All right, so a spinning drum that just the people are on the inside of. The floor is kind of the inside of that drum, and as the drum spins, your inertia wants you to do, so if this is you right here, your inertia wants you to travel in a straight line. But what keeps you from doing that? Right, the inside of the drum. But the inside of the drum doesn't push backwards, it pushes towards the center. Okay, so the normal force of your inertia kind of pushing you against the inside of the drum pushes back towards the center and feels like gravity. It isn't real gravity because it's not caused by the mass of something else, okay? But it feels that way, right? Because really on Earth, it's the same force that we feel. We don't feel gravity. We feel the normal force of the floor or the ground pushing back on us. So this feels just like gravity. Okay? And we can change it depending on how big that drum is or how fast it spins. Okay, so if you go to Mars, you would have it spin maybe at Earth gravity, and then maybe you'd back it off a little bit because on Mars the gravity is going to be 1/3 of what it is on Earth, and maybe you want to get used to how that feels so that when you move around you don't fall down and things like that. And then on the way back, when you get home, you got to look good on the beach, so you crank that puppy up down like 2G. Okay, so everything's twice as heavy as normal, and just walking around and lifting up your plate to eat is a good workout. Okay, and then you get all buff for when you come back. No. No, you wouldn't, because you would still have inertia, right? You'd still be wanting to go that way, so you'd still have inertia. Okay, because I'm going to show you a video. It's actually a clip. How many people have seen 2001: A Space Odyssey? It's older than me, so it's like older than dirt. Okay, but it's an older movie where Arthur C. Clarke, who's written lots of science fiction books and actually worked for NASA for a while, kind of shows how these things would work. Now, this thing was filmed in the 60s. Okay, so imagine all the effects are practical. There's no CG or anything in that, and they've done a good job of showing what it would look like for the most part to be in one of these spinning modules. Nowadays, for those movies, they'll make a spinning drum for part of the shots, but most of the shots are just going to be CG. Okay, because it's easier and less expensive to do that. All right, so this is how we would set this up. So what we want is for the centripetal force provided by the inside of the drum to feel like we're at home experiencing the force of gravity. Okay? Now, the force of gravity is not really there. We're using the what force? Normal force. So really what we're saying is that Fc equals the normal force, but that's still going to be equal to m times g. So what we'll have is mv squared over r equals m times g. Right? And then, a question could ask you any number of things. They could give you the radius and ask you what's the speed that the cylinder has to spin at, or they could give you the speed of the cylinder and ask you for its radius, or give you speed and radius and ask you how heavy you would feel. Okay, something like that. There's any number of ways that a problem like that could go. Okay. All right. So if we're looking at this, okay, we said the surface of the space station provides this force. So this is actually a picture of one of the shots from 2001: A Space Odyssey. They built a full spinning drum to film these scenes on. All right, now remember, they're filming them on Earth, so there is gravity. So the astronauts or the actors could only ever be where? On the bottom or anywhere they wanted as long as they were belted in. Okay, and there is actually a scene where one guy's walking. He's obviously always on the bottom. The other guy's actually belted into the chair, and he goes around. Okay, as the thing goes, he would actually be upside down. Of course, they don't show him when he's at the top because it would look like he was upside down. Right? They only kind of catch him as he comes back into frame, focused on the guy who's walking at the bottom of the drum. Okay, so for the most part, they do a pretty good job of making that look realistic. But there are some times when you can tell that they're actually on Earth, because once in a while you'll catch them walking a little bit too fast or a little bit too slow, and the drum will get ahead of them or behind them, and then they'll look like they're walking uphill or downhill. You'll see them lean. Okay, if this was in space, you'd never lean. And you can catch that in basically any science fiction movie where they've got this. You'll catch one of the actors doing that. Okay, because they'll just get a little bit ahead or whatever, and they just don't get a good enough shot, and you'll see them lean or lean forward because they're actually on Earth filming this and not in space. Okay, so that's what we would have there. Okay, I'll show you a couple of those clips. If you haven't seen 2001: A Space Odyssey, it's a cool movie, but it's weird. It's very confusing. It's like 3 hours long, and there's less than 18 minutes of dialogue in the whole movie. There's lots of sounds of people breathing in their space suits and stuff like it's directed by Stanley Kubrick, who's weird. Like he directed The Shining and movies like that. He's weird. Okay, but yeah, the movie is quite cool. It's based on a good book. The book is better than the movie, but the special effects that they used, the sets they built were groundbreaking for the time. People's minds were blown when they saw this movie, like they were when they saw Star Wars for the first time. Okay, those special effects were all just kind of mind-blowing. Okay, so I'll show you some of those here. All right, so we kind of seen now how that works, okay? And then if this would be like a sample problem that we might get for artificial gravity. So we've got this spinning drum that has a radius of 1,700 meters, so a really, really big one. Okay, we need to figure out what speed it needs to move at in order to make astronauts feel like they're experiencing their normal Earth weight. So we said that means the centripetal force needs to feel like the force of gravity. Even though it's not actually gravity, it's just normal force, we want it to feel like gravity. So we're going to have mv squared over r equals m times g. The only thing they gave us in the question was the radius and Earth weight. All right, so we would need to know 9.81. All right, so we're trying to solve for how fast this drum needs to spin at. So we're going to multiply both sides by r. What happens to m? Yeah, and it should, right? Because not all astronauts have the same mass, but they all should feel like they're at home. Okay, so mass just cancels out, and then we square root. So v will equal the square root of gur this time, and not mu-gur, okay, like it was before. All right, so v will equal then the square root of 9.81 times 1,700. Right, it's a pretty big space station, so probably going to have to spin fairly fast. All right, so it's got to spin at almost 130 meters per second. Right. Now, you wouldn't notice that if you were on the inside of it, okay, because you'd be moving at the same speed. Okay, so it would be irrelevant. It's not like it would be windy or anything. Everything inside would be moving at the same rate. Okay, if you were outside, that could be a problem. And there is a scene on that in The Martian, okay, where they're bringing in that supply module to the Hermes, okay, and he's on the outside and he's moving around on the outside. Like, you would have to stop the gravity part from spinning if anyone was working on it, because if they were to be thrown off of it, you'd never retrieve them, right? Because they would be going way too fast. Okay, it just wouldn't be safe to have that thing spinning like that if someone was doing an EVA.
If you were in the center, then you jump, so you go right to the other side.
No, you wouldn't. Like, because you would have this motion here, you would be like a projectile.
Okay.
Yeah. So if I jump straight up and down, I'm still going to do, right? I'm gonna essentially, well, actually, I won't even arc. I might fall behind a little bit, for air resistance or whatever, but mostly I would just go straight up and straight back down again. Now, if I tried to propel myself a little bit, I might be able to jump a little further.
Yeah. Jump back again?
Yeah. Yeah. It's not going to change much. You might notice a small change in what you're able to do. But the thing would be, if I jumped towards the center, I would have, like, gravity would decrease the closer I got to the center. Okay, so that makes sense to everybody? How that one works? They're pretty straightforward problems. Anything that's artificial gravity, the centripetal force equals gravity. Okay, that's what we're looking at. Okay, so there's been some ideas here. Arthur C. Clarke, the guy who wrote 2001: A Space Odyssey, also wrote a series of books, the Rama series, and it's about this cylindrical spacecraft that comes into our solar system several times, kind of studying, and people get on board and they see the inside of it. But having a ship be a big cylinder is one of the ways to overcome this issue with having only part of the ship spin. If you make the whole ship one big cylinder, then the whole ship can spin. Okay, and then you don't run into these angular momentum issues that you would run into if only part of the ship was spinning. And so he said, yeah, the idea is the whole ship spins and it's one big cylinder, and then you would have lights that would run down the center, or have them divided up, and those would be your light source for the inside. You could have plants growing. You could even have water on the inside. Okay, and in fact, in his book, they have what they called the cylindrical sea. It was this body of water that went around the middle of the spacecraft, and it just stayed there, right? Because it's just like everything else; it's being thrown against the inside of the cylinder, and the cylinder pushes back, and it stays there, just like anything else would. It's pinned there because of the centripetal force. Okay, and so it could all kind of work. The issues would be when the spacecraft would speed up or slow down. Okay, because if you have a fluid and the ship starts to slow down, what does the fluid do? Right, it would keep going. So what they had essentially said is, here's kind of the edges of the cylinder. Okay, so we'd be looking at it like this. So the water would go around the middle like this, and there would be a cliff on the front and a way bigger cliff at the back. Okay, so this is the direction that the spacecraft would normally travel. So if it's accelerating to go faster in a forward direction, it can do that a lot better than it can slowing down, because the cliff on this side is smaller. Okay, if it slows down too fast, the water will slosh over the cliff and onto the front part of the ship. Okay, but if they're accelerating in a forward direction, the cliff is way taller, so the water wouldn't spill over. They could accelerate a lot better in that direction. Okay. Well, because most of the time you probably wouldn't need to worry about the slowing down part, or you would flip the ship around, right, and have it slow down that way, right, because maybe you only have engines on the one side. Okay, so that's the idea, and this would be kind of how you might make a generational spacecraft. At the end of Interstellar, there's a shot of the inside of one of these kind of generational spacecrafts. It would be a big cylinder, and you could put a lot of people inside. You could have dirt. You could grow your own crops because you'd have light. Okay, all of those kind of things. The only issues would be around the water cycle. Warm. Okay, you get your water evaporating, hot air rises. Okay, but it's artificial gravity. So the hot air will rise, but it'll only go where? To the middle, which means you get cylindrical clouds down the middle of the spacecraft. Okay, it would be hard. The rain. How would you get the rain to fall out of those clouds? They're at the center, where there's no what? Where there's no gravity. Okay, so what they said would likely happen is they would have to have drainage at either end of the spacecraft and periodically slow the spacecraft or speed the spacecraft up in order to have all that vapor move to the ends where it would hit the end and then be kind of thrown downwards. Except it wouldn't look like a waterfall. Why not? Well, this is the end of the spacecraft, right? It's a big cylinder, so each end would be a big circle. If the water hits here in the middle and this thing is spinning, the water will do this. You'd have a curved waterfall at either end of the ship. Because of, remember you learned this in Science 10, what was that called? It's why the prevailing winds happen, starts with a C. No. The Coriolis Effect. Does you remember that? And Coriolis Effect, this is the Coriolis Effect. Okay, you'd have, the water trying to move down, but it's moving down on a surface that is spinning, and so its path would be curved. We talked about that when we were in Science 10, we were talking about the prevailing winds, right? Hot air rises and the earth spun underneath it. That's what caused the patterns of prevailing winds. Okay, it was that Coriolis Effect. Okay, same thing would occur there. So some kind of funky things would happen within the spacecraft that maybe we haven't completely worked out yet. All right, so that's it. That's what we got on artificial gravity. So tomorrow, I will teach you about vertical circular motion. Friday, we're going to be doing a lab, okay, on the effect of centripetal force on speed. Okay, so that'll be coming up on Friday. What I want you guys to do your remainder of class is finish up the centripetal force problems from the worksheet that we were working on the other day. Okay, so I'll put those back up on the board, but that's what I want you to finish up, okay, because you still got about 10 minutes or so left here.